Hello, welcome to Key in Motion's course on understanding electricity and electronic devices. Today, we're going to be talking about bipolar transistors. So today's class, we're going to be covering the NPN transistor, and we're going to see how currents and voltages flow in a transistor. We're going to see what saturation is in a transistor, and we're going to see one transistor configuration, which is called the emitter follower circuit. All right, so let's start with the NPN bipolar transistor. It is a three-terminal device. The three terminals are called collector, base, and emitter, right? This is the symbol here in blue for the transistor. The one with the arrow is the emitter. The one with the on the other side is called the base, and the one that is like the emitter but without an arrow is the collector. Okay, so make sure you know exactly what these names are, because we're going to be using them over and over in transistor circuits. So emitter, the one with the arrow; collector, similar one without the arrow; and the base is the one that is on the other side of the bar. Okay, there's several pictures here showing how a transistor looks like. So this is one of the most common packages for transistors, for what we call small signal transistors. This is a power transistor. It has a metal tab here to attach a heat sink. This is another style of power transistor with a heat sink. These down here are surface mount. These two are surface mount packages of power transistors, right? They have two terminals here, and the third terminal is the tab here. This one is usually soldered to a large pad of copper on the circuit board, and that large pad of copper acts as a heat sink. About which terminal is which, like out of these three, which is the collector, which one is the base, and which one is the emitter, we cannot know for sure just by looking at the device itself, right? Check the data sheet, because each transistor has its own terminal configuration, and even the same transistor can be had in different terminal configurations. Okay, so make sure you check the data sheet for the specific device that you have. When you check the data sheet for the pinout configuration, you will find something like this, right? This small signal transistor case that is used in through-hole mounting is called a TO92 case, right? And this is very, very, very common. So it may come with the terminals straight or with the terminals bent like this, and spaced a little bit more. In any case, the data sheet for this particular transistor is telling us that the terminals are labeled 1, 2, and 3. And when you come over here, you find out that the number 1 is the collector, the one on the left. Number 2 is the base, the one in the middle. And number 3 is the emitter, the one on the right. Let's talk a bit on how voltages and current are in a transistor and a transistor circuit. Here's the symbol of the transistor again for reference. And keep in mind that the base and the emitter work as a diode, okay? So if you consider these two terminals only, you can use these as a diode pretty much. Now, the collector current is much higher than the base current by a factor of beta, or HFE. You will find, classically, this was called the beta parameter, but in all the data sheets, you're going to see that reference as HFE. Anyways, beta can be in the range of 100 to 300 for a small signal transistor. So we could consider this device, which is a three-terminal device, as an equivalent circuit where we have a diode between the base and emitter, right? And we can have a base current flowing through this diode. And this base current is going to be controlling the collector current. So this device works as having a constant current source between the collector and the emitter, whose value is beta times the base current, okay? And remember, beta is maybe 100, 200, or 300, right? So the current through the collector is many times higher. If we put numbers here and consider beta or HFE of 100, maybe the base current is 1 milliamp and the collector current is 100 milliamps, right? 100 times bigger. And the emitter current is going to be the sum of the two. It's going to be 100 plus 101 milliamps. Because the base current is so little compared to the collector current, we normally consider the emitter current being the same as the collector current. So approximately, the base current is going to be 1 milliamp, the collector current is going to be 100 milliamps, and the emitter current is going to be also about 100 milliamps, okay? This is a simplification that allows us to make calculations simpler without introducing too much error, okay? So let's consider this example here. We have a circuit with a transistor here connected to a resistor. The collector is connected to a resistor of 330 ohms and then to a 5-volt supply. And the base is connected to a 47 kilo ohm resistor to the 5-volt, to the same 5-volt supply. So what is the collector current and voltage if beta is 100? Okay. So we start by looking at what's going on at the base, right? So we have the base connected to 47 kilo ohms to a 5-volt supply, and then the emitter connected to ground. And we know that the base emitter junction is called acts as a diode, right? So this means that if current is flowing through the base and to the emitter, the voltage at the base is going to be the same voltage we would have on the diode through which current is flowing, so about 0.7 volts. And that will allow us to calculate the current through the base. So the current through the base is going to be the voltage here, 5 volts, minus the voltage here, 0.7 volts, divided by 47 kilo ohms, and that ends up being 0.09 milliamps. Now, once we have the base current, right, 0.09 milliamps, we can calculate the collector current as beta times the base current, right? And we're seeing here that beta is 100. So that results in a beta of, in a collector current of 100 times 0.09 milliamps. So that will result in a collector current of 9 milliamps, okay? So if 9 milliamps are flowing through the collector, they are also flowing through this resistor. And if we want to calculate the voltage here, we can apply Ohm's law and calculate the voltage drop on the resistor. That's going to be 9 milliamps, which is the collector current, times 330 ohms. And if we do 5 volts minus whatever we lose on the collector resistor, we end up with a collector voltage of 2.03 volts. Okay? Now let's repeat the previous problem, same circuit, but let's assume beta is 300 now. Again, the base current is going to be 5 volts minus 0.7 divided by 47 kilo ohms. So nothing changed there. It's 0.09 milliamps. Now, the collector current is still beta times the base current, but in the previous problem, beta was 100, and in this problem, we want beta to be 300. So the collector current now is going to be 300 times 0.09 milliamps, and that's going to end up being 27 milliamps, okay? So nothing changed in the circuit, but we put a transistor with a higher beta, and that will produce a higher collector current. Now, if we want to calculate again the voltage at the collector, it's going to be 5 volts minus whatever we're losing on the resistor, okay? What we lose on the resistor is 27 milliamps times 330 ohms. If we do the math, we will end up with a collector current of negative 3.91 volts. And this negative sign here should be a clue that something is maybe not quite right, okay? And we're gonna have a more detailed look at what's not right in the next section. So we're gonna study transistor in saturation. Now, what is saturation when talking about transistors? The minimum collector to emitter voltage in a bipolar transistor, if current is flowing through the collector, is usually about 0.2 volts. It's low, but not quite zero, and certainly not negative. Okay. So any calculation resulting in a lower voltage when measured between collector and emitter, this means that the transistor is in saturation. So it cannot, so the collector voltage cannot really go any lower. And this usually happens when the circuit cannot deliver the current that the transistor wants. So in the previous slide, we had an example where the transistor wanted to pull 27 milliamps to the collector, but the voltage of the supply, the 5 volts on the supply and the 330 ohms resistor, make it impossible for 27 milliamps to flow through that branch, okay? So in the previous example, really the voltage in the collector was not negative 3.91 volts, but it was actually 0.2 volts or something closer to that, which is the transistor's collector to emitter saturation voltage, okay? So to complicate things a little bit more, beta or HFE is not a control parameter. So data sheets provide only a minimum value for beta, and sometimes a typical value, but rarely a maximum value for beta. And the spread is very high. And a transistor with a minimum beta of 100 will have an actual beta of 300 and saturate if used in the previous circuit. So what I'm trying to say here is, because we don't know exactly what beta is, and beta can vary a lot within a transistor with the same part number, you cannot really know in the previous circuit whether that transistor will be saturating or not. So you cannot know whether that transistor is going to be acting as a current source or saturating at 0.2 volts collector voltage, okay? This is an example taken from an actual transistor, and 2N2222. And these are the on characteristics, and one of the main ones that appears here is the DC current gain. So it gives you the DC current gain. The symbol is HFE, which is the parameter that we've been calling beta. Okay, and this is given at different values of collector current. So at 0.1 milliamps of collector current, HFE is guaranteed to be a minimum of 35, but there's no maximum value for it. At 1 milliamp collector current, beta is going to be 50 milliamps. At 10 milliamps, it's going to be 75 value of beta. At 100 milliamps, it's going to be somewhere between 100 and 300, right? So this is the only condition when the manufacturer is giving an upper limit to HFE. In these other cases, the manufacturing is not guaranteeing any maximum value for this. All right. So not only we don't know what the maximum value of beta is, but it varies a lot depending on the conditions of collector current. The bottom line is you cannot really know for sure what your value of beta is, but you know it's a fairly high value. So that means in the worst case here in this table, the collector current is going to be 35 times higher than the base current. So that is the bottom line. Let's have a look at a different configuration of transistor here, a transistor circuit. This circuit here is called an emitter follower. Okay, let's see how this works. So we have VCC, which is a power supply supplying some collector voltage. Okay, let's assume this is, say, 10 volts for now. Okay, or something along those lines. Now here we have a V in an input voltage, right? Some kind of signal that we are feeding to the base of the transistor. And we're taking the output from the emitter of the transistor. And we have here a resistor that is representing whatever next circuit is following this transistor. And let's assume that this resistor is making the emitter current to be something around 100 milliamps. Okay, so let's try to figure out what the voltages and currents are here. The output voltage is easy, right? Because we said that the base emitter terminals work as a diode. So if there's actually current flowing here, we have 0.7 volts at this point, less than what we have at the base, right? Now, we mentioned that because the base current is much lower than the collector current, and the emitter current is the sum of these two, the emitter current is approximately the same as the collector current. So the emitter current is the current flowing through this resistor. So it's going to be about 100 milliamps. The collector current is going to be about 100 milliamps as well, right? And the base current, which is the current delivered by this source, is going to be the output current divided by HFE, or the DC current gain, or the beta of the transistor. Now, let's assume that beta is 100, okay? So if beta is 100, the current supplied here, the input current to this transistor or to this circuit, is going to be about 1 milliamp. Okay, and the rest of the current to provide 100 milliamps to the load is coming from the collector, from this supply, from this VCC supply, and through the collector to the emitter. Okay, so this is going to be about 99 milliamps. So let's see how we can use the circuit that we just saw on the previous slide to improve the old voltage divider that we studied several classes ago. Let's consider this circuit here with a 12-volt supply and a voltage divider provided by these two resistors, 6.8 kilo ohms and 4.7 kilo ohm. We will call VD the voltage at the output of the divider. Okay, so if we keep this switch open and we do the math for this voltage divider, we will end up with 4.9 volts here for VB. Okay, this is just by applying the equation that we studied several classes ago for voltage divider. Now, what happens when we close the switch? Well, we saw that again in the same class, that this will cause a drop in voltage, and it can be fairly high, that drop, right? When you close the switch, you can consider that the 4.7 kilo ohm and the 1 kilo ohm resistor are in parallel. So these two resistors combined in parallel end up being around 820 ohms. So that means that the intended resistor here that originally was 4.7 kilo ohms, now it's 820. And that will result in a much lower voltage in VB. So VB is going to drop from 4.9 volts with the switch open to 1.29 volts with the switch closed. Okay, so let's see how we can improve this situation. We ideally want the voltage here not to be dependent on what we connect over here after the switch. Okay, so let's modify this circuit by opening it first and then connecting a transistor like this. If you have a look at this, this is the emitter follower transistor circuit that we had in previous slide, right? With the collector connected to the positive of the supply and some input voltage coming to the base and taking the output from the emitter. This is what we're going to be doing now. Let's assume this transistor has a DC current gain or beta or HFE of 150. With the switch open over here, there's not going to be any current flowing, right? So the voltage here is the same as in previous case, the 4.9 volts. That's what we have here. Now at the emitter, because this acts like a diode, we said that the voltage at the emitter is going to be about 0.7 volts below the voltage at the base. So if we have at the base 4.9, at the emitter, we're going to have around 4.2, okay? Now, what happens when we close the switch? When we close the switch, the 1 kilo ohm resistor here is going to be taking current from the transistor, but that's going to be provided, like we said, through the collector, right? From the power supply to the collector and to the emitter. And the current, the base is gonna increase, but only very slightly. In this case, if you consider a beta of 150, the base current is gonna be 150 less than the current here at the emitter or at the load, okay? And that greatly reduced current that we're now taking from the voltage divider. That means that the voltage divider is dropping from 4.9 volts to 4.81. Remember before it was dropping from 4.9 to 1.29, right? So it was dropping like 3.6 volts, and now it's dropping at 0.1 volt. This drop that we have at the base circuit is reflected also at the emitter. So the emitter drops from 4.2 to 4.1. Okay, so again, 0.1 volts here. This means that the transistor is isolating to some extent what's happening at the emitter from what's happening at the base. So we can take a lot more current from the emitter, and that's not going to be affecting pretty much at all what happens on the base, right? In this case, the voltage dropped only for 0.1 volt. Now, the drawback of this, if you want, is that your emitter voltage is 0.7 volts less than the base from the start, okay? But you could adjust these resistors, the 6.8 and the 4.7, to provide an extra 0.7 volts here and to compensate for the drop that you're going to have between base and emitter. So the same idea could be applied for a voltage regulator. If you remember from our classes about Zener diodes, The Zener diode by itself was very poor at delivering current, right? So we were limited in the example, I think, from 0 to 50 or 80 milliamps. And that was it, right? If we add a transistor here in the emitter follower configuration, we will be able to deliver current in the range of maybe 0 to 1 amp, right? Because the voltage regulator with the zener and the resistor only have to deliver 100 times less to the base, right? So maybe something in the range of 0 to 10 milliamps, which is well in the range of the 0 to 80 milliamps that we calculated we could deliver. So let's summarize what we saw today. Transistors are three-terminal devices. The three terminals are called emitter, base, and collector. The base and emitter work as a diode, right? You normally have those forward biased with current flowing there. And as a diode, you would have a voltage drop of around 0.7 volts there. But the most important thing about the transistor is that the collector current is controlled by the base current, and it is many times higher. We also saw the emitter follower circuit that allows the output voltage to follow the input voltage, although about 0.7 volts below, but it takes very little current from the base or from the input source, right? And that allowed us to make the improved voltage divider and the improved voltage regulator with the Zener diode. And the other thing that we have to keep in mind is that if the external circuit cannot provide enough current to the collector of the transistor will saturate at about 0.2 volts. Okay, that is all for today. I hope you enjoyed the class and see you next time with more about transistors. Thank you. Bye-bye.